So in our last topic of geometry, we started our third chapter, circle, and in that topic we have studied some activities. Also we have studied circles passing through 1 point, 2 point, 3 points. Now also we have studied secant and tangent. Now we are going to learn tangent theorem, and we will solve examples on that tangent theorem. So first we will prove that theorem, tangent theorem. Tangent theorem. The statement of theorem is a tangent at any point of a circle is perpendicular to the radius at the point of contact. Now here, the circle of center O, line L is touching the circle at point A. That means point A is the point of contact and OA is the radius. That means this line L is perpendicular to the radius. That means this tangent is perpendicular to radius. We have to prove this. For that, here given things are line L is a tangent to the circle at point A, and OA is the radius of the circle. Point O is the center of the circle and A is the point of contact. These are the given things. Now we will prove this. Now here we have to prove that line L perpendicular radius OA. Now for the proof of this theorem, we will use indirect method. There is an indirect proof of this method. That means first we will assume that line L is not perpendicular to OA. We will assume that line L is not perpendicular to OA. That means OA is not perpendicular to line L. Then suppose segment OB is perpendicular to line L. Suppose segment OB is perpendicular to this line L. If OA is not perpendicular, then another segment from O must be perpendicular, and suppose that segment is OB. Now consider this, the modified figure next. Now here of course B is not same as A. Now take point C on this line. Take point C on this line such that A dash, B dash, C. So in that means point B is between A and C. And take distance AB is equal to BC. That means this distance AB and distance BB is equal to same, and that is AB is equal to AC, or now here after this construction we have two triangles here. Which two triangles? Triangle OBA and OBC. Now in triangle OBC and OBA, now here segment BC congruent segment BA. See here, this segment BC is congruent segment BA. The reason is that construction. Now angle OBC congruent angle OBA. Angle OBC congruent angle OBA. This one is each right angle. Because we have assumed that OB is perpendicular here. So here angle OBC and OBA are right angles, therefore they are congruent. And OB congruent OB. Reason is common segment. Therefore, triangle OBC congruent triangle OBA by side angle side test. Now these two triangles are congruent, therefore their corresponding sides are also congruent. Therefore, OC is equal to OA. Corresponding sides of congruent triangles. So here we came to conclusion that here OC is equal to OA. Okay, but point A is on the circle, but OA is a radius. That means point A is on the circle. Therefore, OA is the radius. And OA and OC are equal, congruent. Therefore, point C is also on the circle. But segment OA is radius. Therefore, segment OC must be radius. Okay. And therefore, C lies on circle. That means line L intersects the circle in 2 points. That means A is on the circle, C is on the circle. According to our assumption, A is on the circle, C is on the circle. That means this line intersects the circle in 2 points A and C. But line L is tangent. It is given. Line L is tangent, and we know that the tangent intersects the circle in only one point. That means line L intersects the circle in 2 points, and line L is a tangent. It is given, and therefore it intersects the circle in only one point. Therefore, our assumption that line L is not perpendicular to radius OA is wrong. Therefore, line L is perpendicular to line radius OA. Therefore, line L is perpendicular to radius OA. In this way, we can prove. This proof is on page number 51. You go through that statement, theorem, and write down in your notebook. Now, we will study the converse of tangent theorem. That means converse of this tangent theorem. The converse of tangent theorem. Theorem: a line perpendicular to a radius at its point on the circle is a tangent to the circle. Suppose here in the figure Mn is the radius and point N of the radius is on the circle. This line L is perpendicular to radius at point N. These are the given things. What are the given things here? M is the center of the circle. Segment Mn is a radius. Line L perpendicular segment Mn. These are the given things. And we have to prove that line L is perpendicular, the line L is tangent to the circle. Now, to prove that, we have to take one point, any point on this line L other than L, and suppose that point is P. So here take any point P other than N on the line L and draw segment PM. Segment PM. Now see here, we have taken any point on line L other than N and we have joined segment MP, and it is given that Mn is perpendicular to line L. That means here this is MNP is right angle and this triangle is right angle triangle. Triangle MNP is right angle triangle, and in this right angle triangle PM is the hypotenuse. PM is hypotenuse, and you know the property of right angle triangle that the hypotenuse is the greatest side of a triangle. That means this hypotenuse, length of this hypotenuse is greater than length of Mn, length of MP. That means here segment MP greater than segment Mn. That means this distance MP is greater than this distance MN, and MN is radius. That means this distance MP is greater than this radius. That means this point P do not lie on the circle. That means point P do not lie on the circle, and therefore no other point except point N of line L is on the circle. Line on the line L, point N is there, and only this point N is on the circle. No other point except point N of line L is on the circle. Therefore, line L, this line L intersects the circle in only one point. In only one point, that means in point N. And therefore, line L is tangent to the circle. Now, according to the definition, line L is tangent to the circle. That means the line which intersects the circle in only one point, that line is called tangent to the circle. Therefore, line L is tangent to the circle. So, this proof is on page number 52. You go through that proof and write down on in your notebook. Now see here, A is the center of the circle, and point T, this point D is in the exterior of the circle, and we can draw tangent to the circle from point D. How many tangents can we draw from the exterior point to the circle? So we draw the tangents from point D. This is one tangent. This is another tangent. Suppose these tangents intersect the circle in point P and Q. That means we can draw only two tangents to the circle from its exterior points. Point D is in the exterior of the circle, and from point D we can draw only two tangents. Here in the figure, tangent CD and QD are two tangents. These are tangents, and segment PD from P to D, this segment is called tangent segment. QD is called tangent segment from P to D, tangent segment, from Q to D, tangent segment. Now we will learn the next theorem, the theorem of tangent segment theorem. Now here, tangent segment theorem. The statement of theorem is tangent segments drawn from an external point to a circle are congruent. That means these are tangent segments, DP and DQ. We have to prove that these two segments are congruent. So here, given things, here A is the center of the circle, and tangents PD and QD are tangents drawn from the exterior point of the circle, touches the circle, at P and Q. These are the given things. Now we have to prove that segment DP congruent segment DQ. For that, we have to draw the radii of the circle. Draw radius PA and radius AQ, and join AD. Now here we get here two triangles. These two triangles, triangle APD and EQD. Tangent segment, and now we will complete this theorem. So here in triangle PAD and QAD, triangle PAD, QAD, segment PA congruent segment dash, segment PA congruent segment QA, radii of the same circle. Here segment QA, radii of the same circle. Now segment AD congruent segment AD. Here region is common segment. Now see here, angle APD congruent angle AQD is equal to 90. Each angle is of 90 degree. Tangent theorem. That means if this angle P and Q are 90 degree, that means both the angles are right angle triangle. Angle PAD, angle QAD are right angle triangle, and AD is their common hypotenuse. AD is the hypotenuse, and therefore triangle PAD congruent triangle QAD by hypotenuse side theorem. Hypotenuse side test. Therefore, segment DP congruent segment DQ, reason is that corresponding sides of congruent triangles. Corresponding sides of congruent triangle. In this way, we can prove that tangent segment drawn from external point to the circle are congruent. Now in next period we will solve examples on this theorem.